In this section, we're looking at vectors in a plane. A vector, unlike our scalar quantity, and a scalar quantity is one which has only a magnitude, such as length, time, and speed. A vector is two-dimensional in that it has both magnitude and direction. We use a directed line segment to represent our two-dimensional vector. So here we have our initial point, P1, P2, and we have a terminal point. This is where our vector is heading to. And it's represented by Q1, Q2. P1 and P2 is the equivalent of our X1, X2 in our rectangular coordinate system, which is two-dimensional. Our line segment can be represented as V, so in lowercase letters, or we can write this PQ with this arrow over the top indicating the direction that it's going from P to Q. To find the magnitude of our vector PQ, it's written as PQ with an arrow with the double lines on both sides, or as the magnitude of V, or vector. Now, because this is a line, the magnitude is just the length of the line. So we can use our distance formula to find the magnitude of our vector. So the magnitude of PQ would be equal to the square root of Q2 minus P2 squared plus Q1 minus P1 squared, and then we find the square root of that. That's the equivalent of our distance formula. To define the direction of our vector, there's a couple of things we can do. One is to find the slope using Q2 and P2 as our Y2 and Y1, and Q1 as P1 as our X2 and X1, and use our slope formula. So, two vectors with the same magnitude and directions are equal. So if we have two directed line segments and they have the same magnitude from our formula, and they have the same direction, possibly the same slope, then we know that those two vectors are equal. We're going to demonstrate this using a couple of examples. So in this example, we're being asked to show that the vectors u and v are equivalent. So here we have u going from the point 0, 4 to the point -3, -4, and v going from the point 3, 3 to the point 0, -5. Now, to show that both vectors are equivalent means they have the same magnitude and the same direction. So we can proceed to find the magnitude of u and the magnitude of v, and the slope of u and the slope of v. Going back to our formula, the magnitude of u will be equal to the square root of -4 minus 4 all squared plus -3 minus 0 all squared. So remember, this is our P and this is our Q, so it's Q minus P. So this becomes, once we simplify, the square root of 73. To find the slope of u, once again, this would be -4 minus 4 all over -3 minus 0. So this is -8 over -3, which simplifies to 1/3. Now we have the slope of u and the magnitude of u. We will go ahead and find the magnitude of v and the slope of v. We're going to do the same thing. To find the magnitude of v, here's our point P and our point Q. So it's Q2 minus P2, -5 minus 3 squared, plus Q1 minus P1 squared, and this simplifies to give us the square root of 73. So here we can see that they both have the same slope, same magnitude. Now let's find the slope of v. It would be -5 minus 3 all over 0 minus 3, which also give us the same slope. So we can see that they have the same magnitude and same direction, therefore they are equivalent vectors. Now, for a vector, it's often more convenient to think of a vector in its standard form or standard position. Standard position is when a vector has an initial side or point P at the origin. Now, to find the standard form, we call this the component form of a vector. So if we have 2 points, the initial point being P1, P2, and our terminal point being Q equal to Q1, Q2, then we can find this component form. So V is equal to PQ, and this is how we find our component form. It's Q1 minus P1 and Q2 minus P2, and it's written like this, these symbols which kind of look like a less than and a greater than symbol at the end, and it's written as V1 V2. So the component form of V would be V1 V2. Now to find the magnitude of PQ or V using the component form, it's just the square root of V1 squared plus V2 squared. Now a unit vector is one in which the magnitude is 1. So if we did all this work and this ended up being 1, then that would have been a unit vector. We also know that two vectors are equivalent if their individual components are equal. So if we have a vector V with V1, V2, and we have a second vector U with components U1 and U2, then we know these two vectors are equivalent if V1 is equal to U1 and V2 is equal to U2. So here we have a couple of examples of finding a component form of a vector. And we're also going to find the magnitude. So we're given our initial site, so here's our P and this is our Q. We know the component form of our vector V1, V2 is equal to Q1 minus P1, so it's -1 minus 2, and Q2 minus P2, so it's 4 minus 2. So this gives us -3 and 2. To find the magnitude, it's V1 squared plus V2 squared, and we find the square root of that, and that comes out to be the square root of 13. Here we're told that our initial side is 111, and that our terminal side is 93, point that is. So to find our component form, it would be Q1 minus P1 and Q2 minus P2. So here we have 9 minus 1, which is 8, and 3 minus 11, which is -8. So here we have the component form of this vector. Now to find a magnitude, it would be V1 squared plus V2 squared, and we find the square root of all that, which comes out to be the square root of 128. When we simplify this radical, we get 8 radical 2. In this section, we're looking at two fundamental vector operations. The first one is scalar multiplication, and when we talk about multiplying by a scalar quantity, we're talking about multiplying by a constant, and this constant is a real number. So if we have our vector u, which is component form is u1, u2, when we multiply that vector u by a constant k, this is the same thing as multiplying each component by that constant k. So this becomes k times u1 and k times u2. If we look at this graphically, here we have our vector u. If we were to find 2u, this is the same thing as twice the length of u, since it's going to change each component by 2. So 2u would actually be twice the distance. So here we would have 2u. If we wanted to find -2u, with the same distance, however, we're going in the opposite direction. So this will be u and u, so this will be -2u. Here in the second of our vector operations, we're looking at scalar addition. If we have two vectors u, which has components of u1 and u2, and our second vector v, which has component v1 and v2, our scalar addition of u and v is simply u1 plus v1 and u2 plus v2 to give us the components of u plus v. If we look at this graphically, here we have u and v, our two vectors. To add vectors graphically, we add the initial side of one vector to the terminal side of the next vector. So if we're adding u plus v, means we're adding the v to u, we would move our vector v in the same magnitude and direction. So here this would be our v. To find u plus v, it's the equivalent of, drawing the diagonal of our parallelogram. So here, this piece right here would be u plus v. Now this diagonal here is also known as a resultant of our vector addition. Now we'll look at a couple of examples demonstrating this and our scalar multiplication. Here we're given two vectors u and v, where u is equal to 2, 1 in its component form, and v in its component form is equal to 1, 3. We're asked to find u plus v, u minus v, and also 2u minus 3 times v. First we're finding u plus v, so that becomes u1 plus v1, which is 3, and u2 plus v2, which is 4. To find u minus v, it will be u1 minus v1, so it's 2 minus 1, which is 1, and u2 minus v2, which would be 1 minus 3, which is negative 2. To find 2u minus 3v, first we have to multiply 2 times u, which gives us 2 times 2 is 4, and 2 times 1 is 2, and also multiply 3 times v. So this becomes 3 and 9. Now we can subtract 3v from 2u, so it's 4 minus 3, which is 1, and 2 minus 9, which is negative 7.